Hi peeps. Alright, this is chapter 2, the atom. I just want you to know I have some cheater notes down here, so if you see me looking, don't get panicked. I'm going to give you some visual reference for some of the things we talked about in chapter 2, so hopefully it'll make a little bit more sense, especially when I was talking on the video. So one of the first things we're going to look at is the actual atom, okay? And in the book, we tend to have the nucleus, and then we have the orbital shells that kind of come around, okay? In here we have the protons and the neutrons, and then we have the electrons on the orbital shells, okay? So when we draw it in the book like that, it's nice and flat and two-dimensional, and it's just easier for us to discuss. But realize that when they recognize the atom, it's in constant motion. So realistically, what it would look like is not like this, where it's nice and easy, but you would have a nucleus, and then you would have the orbital shells kind of coming around it like this. So constantly in motion, meaning this is moving all the time. And you have little electrons all over here, all over all the orbital shells like this, which means this is in constant motion. So when we talk about interactions, you're talking about a photon coming through. The likelihood of striking that, it's way more likely than if we think about it like this, and you have a photon coming in, it'd have to hit right there, because if it came in anywhere else, it really wouldn't. So just remember, every time we talk about an atom, you're talking about something like this, where it's constantly in motion, not nice and flat like the book wants us to think, okay? That's the first thing I want to point out. Constant motion with that atom. All right, what else are we going to look at? We are going to look at the fact that when we look at an atom, in the nucleus, we have protons, which are positive, and we have neutrons, which are neutral, meaning they don't have any charge. And then on the orbital shell, if we just give it one shell, we have electrons, which are negative. So protons are positive, electrons are negative, and neutrons are neutral. Right? These are your three subatomic particles. And we find the protons and the neutrons in the nucleus, and those are usually referred to as nucleons. And those, when you add those together, when you add the protons and the neutrons together, that gives you your atomic mass. Okay, so that gives you the weight of that atom. Let's see. The number of protons always is your atomic number. So let's just say that an atom had, let's just say the atom has 6 protons. Then it would always be carbon, because atomic number 6 is carbon. So if it has 6 protons, it's carbon. If it had 13 protons, it's going to be aluminum. Why? Because atomic number 13 is aluminum. So the number of protons is the atomic number. Oops. Protons is your atomic number. Number of protons and neutrons is your atomic mass. And when we talk about an isotope is something that will have the same number of protons but a different number of neutrons. So let's use, let me get rid of this and I'll give you an example. So if we look at tungsten, because that's one that we're going to have to look at. Tungsten has 74 protons, and it has 110 neutrons. So its atomic mass is 184 in a stable atom. But let's say another atom of it had 74 protons, but it had 112 neutrons. Then it would weigh 186, and this would be considered an isotope of tungsten. Okay, so this would be like a regular tungsten atom, a stable tungsten atom. This would be an isotope because it has the same number of protons, but a different number of neutrons. Okay, so isotope, different number of neutrons. That's an isotope. Different number of neutrons, same number of protons. All right, let's talk about the charges and what those mean on an atom. So, when we look at an atom, just go with a little number. Let's say that we have an atom that has, totally making this up, let's say it has 6 protons in there, and it has 2 orbital shells, and it has 6 electrons. Okay, what does that mean? It has 6 protons and 6 electrons. So for each of the 6 positive charges, there are 6 negative charges, which means that these positives and negatives cancel each other out. So this is a neutral atom, or a stable atom. Okay, stable atom. Now, let's say we have the same kind of thing down here, and we have 6 protons, but let's say that we only have 5 electrons. Okay, when we have 5 electrons, so now we have 6 protons and 5 electrons. So what happens? When we cross those out, we can get rid of 5 of those, but we're left with 1 overall positive charge. Okay? So when we have a positive charge, that is called a positive ion. And a positive ion can also be called a cation. So a positive ion or a cation means that there are not an equal number of positive and negative charges, but it has a leftover positive charge. So it's a positively charged ion. How could we get that? One of the electrons would have had to be removed. So when that electron got removed, okay, so let's say we had 6, and one of them was removed, what happens is you're left with 5, so that's a positive ion or a cation. Now, what if you had the opposite, where it gained an electron? Well, if it gains an electron, then it started off with 6 positive protons, and then it had 6 electrons. And let's say somehow something happened and it gained an electron. So now it has 6 protons, but it has 7 electrons. You can get rid of 6 of those, but you're left with an overall negative charge. So now you would have a negative ion. And a negative ion can also be called an anion. Right? So gain or loss of an electron from a relatively stable atom is an ion. You've ionized that atom, and that's what makes what we do so dangerous, because we have the ability to cause removal of an electron, or it could potentially add an electron. So because we can ionize matter with what we use, we create anions and cations. Now, why is that a big deal? Because if you're talking about in the body, when things are multiplying and you're you've disrupted that stable state and you've created an ion and you replicate or duplicate that, that's the potential to cause cancer. So that's what makes what we do dangerous. I'm not saying that we cause cancer every time we make an exposure, but the potential is there to create cations, which are positive ions, and anions, which are negative ions. Okay, so it's the gain of an electron or the loss of an electron. In that case, we'd have to lose 2 because we had started with 6, now we have 5, and if you have 5, it's no longer got a leftover negative charge, it would have a leftover positive charge, and that's a positive ion or a cation. Okay? Alright, now let's look at binding energy. Because we have 2 types of binding energy. We have nuclear binding energy, and we have electron binding energy. So the first thing, when we look at in the nucleus, we said we have positives. We'll just stick with 6 since we like that. We have 6 positive, and then we have neutrons in here as well, which have no charge. Okay, now one of the laws of electrostatics says that like charges repel. So why don't these repel each other? Because of the nuclear binding energy, meaning it's able to overcome the charges. The nuclear binding energy allows that likeness to stop repelling each other and actually causes it to stick together. So therefore, in the nucleus, the reason that all stays together is because of the nuclear binding energy. We have the same thing on the orbital shells, except we call this electron binding energy. Okay, so what's this? This is positive in the nucleus. This is negative. So what will opposites do? Opposites attract. So like charges repel, typically, and opposites attract. And that is one of the laws of electrostatics. Okay, so because of the degree of attraction between the positively charged nucleus and the negative electrons, it holds it together. So the degree of attraction between here and here is stronger than here and here. Remember I said if you had 2 magnets, if these are 2 magnets and I put the same ends together, they're never going to touch. They're going to repel each other. But if I turn one around and I put the 2 together, at some point they're going to go together. There's no way I can keep them apart. So opposites attract, like charges tend to repel. But the nuclear binding energy overcomes that and allows them to stay together. And then on the electron binding energy, that degree of attraction is strong, so it keeps those electrons on the orbital shells instead of allowing them to fly off. All right? And that's important when we talk about X-ray production. Okay, now, last thing, tungsten atom. This is the one that I told you is very important. We have to understand every aspect of this tungsten atom. So we're going to draw this. When we start with a tungsten atom, tungsten has 74 protons, 110 neutrons, has an atomic mass of 184, and it has 6 orbital shells, but I'm only going to draw them on one side, okay? Normally they would go all the way around, but I'm limited. So we have first shell, okay, so we start with K shell, we've got L, M, N, O, and P. So tungsten always has 6 shells, always has 74 protons. Now, the numbers I'm going to give you, you're probably going to ask yourself, well, where did they come from? Somebody way smarter than me came up with them. I'm not making them up. I can't change them. They are what they are when we talk about binding energy. Okay, so we've got 74 protons, 110 neutrons. Now, on K shell, there are 2 electrons. So I'll just draw them like this. On L, there are 8 electrons. M has 18. N has 32. O has 12. And P has 2. So it's 2, 8, 18, 32, 12, 2. So add those up. If you add 2 plus 8 plus 18 plus 32 plus 12 plus 2, so there's 74 electrons, okay? So 74 electrons, 74 protons. This is a stable atom of tungsten. I didn't draw them all out because it would get too crazy, but just know that somebody else has already figured out the configuration of an atom of tungsten. There's 2 electrons on K, 8 on L, 18 on M, 32 on N, 12 on O, 2 on P. Students always ask me, well, why 12 and 2? Why not, why not 9 and 5? Why that? I don't know. Somebody way smarter came up with that, and that's what they say. Okay? The binding energy on these particular shells, if we look at that, the binding energy for K shell is 69.5. L binding energy is 12. M is 3. N is 0.6. O is 0.08. P is 0.02. Okay, so 69.5, 12, 3, 0.6, 0.08, 0.2. That's the binding energy, meaning the degree of attraction between these electrons and these protons is 69.5 keV, or kilo electron volts. So very strong. 69.5 is much higher than 12, right? So the binding energy between here and the nucleus is less. The further we go out, the numbers go down. So the binding energy is strongest at K shell, weaker at P shell. All right? Strong, weak. That's the binding energy that keeps the electrons on their orbital shell. So what do we need to know about tungsten? All of this. 74 protons, 110 neutrons, 6 shell levels that don't change, K, L, M, N, O, and P. The number of electrons on each shell, K has 2, L has, like that, K has, we'll just write it here, is easier, 2 electrons, L has 8 electrons, 18 electrons, 32 on N, 12 on O, 2 on P. Okay, 2, 8, 18, 32, 12, 2. Always and forever, doesn't change. I didn't make it up, that's just how it is. And then the binding energy, 69.5 between K shell and the nucleus, 12 keV between L and the nucleus, 3, 0.6, 0.08, 0.02. The only other thing is when we talk about these shell levels, like K is shell level 1, L is 2, M is 3, N is 4, O is 5, P is 6. Now why did I do that? Because one other thing we talked about in chapter 2 is you can always state the maximum number of electrons that a given shell can hold by using the formula 2n squared. So 2n squared tells you the maximum number of electrons a shell can hold. Can hold. Doesn't mean it will, but it can. So let's just, n is this number right here. It's called the principal quantum number. So that's what you replace in there. So let me give you an example. We're saying K is 1. How many electrons can K shell hold? 2. We've already said that. How could we prove it? Because if we use that formula and K is 1, then we could say 2 times 1 squared. Okay, so if you take 1 times 1 is 1, times 2 means 2 electrons on K shell. Makes sense. How about L? We would plug in 2 and use 2 for L squared. So 2 squared is 4 times 2 would mean 8 electrons. You with me? Let's do the next one. 2 times 3 squared. So 3 squared is 9 times 2 is 18. So far, we're holding true, correct? So far. No, that's the maximum number. 4 squared is 16 times 2 is 32 electrons. Yep. Now, here's where it's going to switch up. Only because this is the maximum number. Doesn't mean it will. It's the maximum that it can hold. So what's O is the fifth one. So if we do 2 times 5 squared, 5 squared is 25 times 2 means it could hold 50 electrons. Okay, it has 12, but it could hold 50. How about P? 6 squared is 36 times 2 is 72. All right, and we only have 12 and 2. Now why the difference? Because this is the maximum number that it can hold. This is how many it's holding. We don't have, if we took 14 away from 74, right here we're at 60. So we don't have 50 to put here. But if we had a higher atomic number element, then we would potentially have more. So what does it mean? It means the shell levels are full up to here, and after that they're not full. All right, remember it also said that the maximum number that the outermost shell can hold is 8. No more than 8, but it could hold less. Is 2 less than 8? Yep, so that's fine. It follows the octet rule. But this formula just says that's the maximum number that a shell level can hold. Roxy decided to put her 2 cents in. Maximum that it can hold doesn't mean it will hold that. Usually K will, because if it has more than 2 electrons, it's going to fill K, and then everything else is going to spill over. So this is the configuration for an atom of tungsten. This is just telling you what the maximum number that shell level can hold. Okay? Hopefully that helps clear some of that confusion up. If there's anything that didn't make sense on here or you need me to reiterate, I'm happy to do so. So, all right, you guys, that's about it. Remember, I'm going to put up a handout for this tungsten atom, but very important that we know everything about that because it will come into play with how X-rays are actually created. Okay, thanks. Have a good day.